Hi, everyone. Welcome to our third and final lecture bite for week 8. Today, we're going to be talking about snow lines and planet formation. In particular, where and why different parts of protoplanetary disks can produce different kinds of planets. So, let's go back again to the first lecture this week, where I talked about we were looking for patterns in the planets in our solar system. One of the first patterns that you can notice if you take a close look is that the inner planets tend to be small and rocky, and they don't have thick atmospheres of hydrogen and helium. But the outer planets tend to be much more massive and much larger with thick hydrogen helium envelopes. Why is this? How could this pattern have existed? And is this something that's a general rule? So, to talk about this and to explain it a little bit more, I want you to remember back to our discussion about Cecilia Payne. And in particular, the idea that the prevailing view in 1925 was that stars were made up of about the same mixture of elements as the Earth. This was why it was a surprise when Payne found that stars had much more hydrogen and helium in them. So, to think about that, I want to consider the idea of why would scientists have thought that the Earth and the Sun were made of the same things? And the idea is basically simple. It is that the sun and the Earth are made of the same gas. So I'm showing here the simulation that we showed in the last lecture bite, in which we have stars that are just formed, and the gas that's surrounding them is falling inwards and essentially coming into a protoplanetary disk. So if we believe that planets form out of accumulation of materials in this disk, and these disks are made out of the same gas, which is mostly hydrogen and helium, as the sun is itself, then why don't all of the planets have the same composition as the sun? So perhaps the real question was not why is the sun made mostly of hydrogen and helium, but perhaps why isn't the Earth made of mostly hydrogen and helium? So the answer is temperature. Temperature is the reason why these planets have different compositions than the sun. And I'll explain what I mean by this. But basically, the idea is that in the sun, it's hot enough that every material is a gas. But in the protoplanetary disk, that's not true. And this is what really matters for forming planets and having these particles accumulate. So, for example, in the sun, everything, including iron, silicon, these are all hot enough that they're above their boiling temperature. So instead of having iron that is a solid or silicon that is a solid, like rocks on the Earth, we have vaporized materials like that. But in the protoplanetary disk, that's no longer true. Very close to the star in the protoplanetary disk, it's still cool enough that rocky materials like iron and silicon can stay solid at temperatures even up to more than 1,000 degrees Celsius. But water is only solid in regions cooler than about negative 90 degrees Celsius. You might be wondering why this is true, since on Earth we know that the boiling point and the freezing point of water are 100 degrees and 0 degrees Celsius, respectively. But of course, things are a little bit different in space, and it's a little bit easier for water to boil in space where there's no pressure, where you're in a vacuum than it is on Earth. So that's why you would have that difference there. So in hot regions of the disk, only the rocky materials will be solid, whereas further away, other materials will be as well. And the key idea here is that when you're trying to build something like a planet, you need for material to stick together. Solids stick together better than gases. So here's kind of a silly example, but think about what water is like in its solid form and in its liquid form. So here I'm showing Will Ferrell throwing a snowball. That snowball is made of ice or snow, which is water in solid form. He reached down to the ground, gathered a bunch of solid together, compacted it, and it stuck together and it stayed together. So the solid water was able to stick together and make a larger conglomeration. But you couldn't do that with gas. So over here on the right-hand side, I'm showing steam coming out of a vent. You could not take that steam, gather it up, put it into a smaller ball and have it stay together, it would immediately disperse. And same with liquid water. So solids are really advantageous for building stuff because they will stick together when they're put together. And in hot regions of the disk, only the rocky materials are in solid form, so only the rocky materials will stick together and therefore build planets. This is why the planets close to the sun, like our Earth, are made of rocky materials, iron and silicon, not hydrogen and helium, and not mostly water. It's because only these planets are hot enough, or only these materials can stay solid at hot enough temperatures to build planets. Yeah, and this is why the composition of the Earth is different from the composition of the sun. The Earth is basically made up of all of the materials that stay solid for the most part, whereas the sun has much more volatile material. Hydrogen and helium make up the bulk of it, which are always in gas form. You can never get them cold enough, really, in the current state of the universe for them to freeze solid. So this suggests a way that planets might form. And the idea is that planets are formed from small, solid particles sticking together and slowly growing larger and larger. So you have two particles that come together to stick together, then another particle of similar size comes together, and you just essentially keep building up more and more material, more and more rocky particles coming together until finally you have a large object that's enough to start self-gravitating and holding itself together. And that's how you build a planet. So this explains why the planets close to our sun, the ones in the hot region of the solar system, are predominantly rocky, because they were only in that region were the rocky materials solid so that they could come together and form planets, which is why you don't get planets with significant amounts of other materials. So what about the outer solar system? This logic isn't complete for that, because it's also not possible to have hydrogen and helium in solid form far away. So what's the key difference between the inner planets and the outer planets? And the answer is it's water. So we're the idea is that the inner planets formed inside of the water snow line, inside of the region where water is going to be in solid form. So here, water is always in vapor form, and it can't really participate in the process of building up these planets. But out here, water is cold enough to be in ice form. And what happens when you have water in ice form, in addition to the other rocky materials, is that the process of accumulating this material is supercharged. All of a sudden, you have much more material to stick together, and it means that you can build these planets much more efficiently and put together all of this material and build bigger cores and build them faster. So, further away from our sun, you can build planets much faster and much bigger. Now, the idea is not to build up the entire planet with rock and water, because as I said earlier, Jupiter and Saturn are mostly made up of hydrogen and helium. Instead, you want to build up enough rock and water so that the planet's gravity is strong enough for it to start sucking in material. So we have this rocky core now, this rocky, watery, icy core orbiting far away inside of this protoplanetary disk, traveling through hydrogen and helium gas. When the mass is big enough, when its gravity is strong enough, it can start bending gas towards it as it passes through and essentially start sucking up all of the gas until it builds up a thick layer of gas on its own. The bigger it gets, the more gravity it gets, the more efficient it is at sucking this gas in. This is what we call runaway accretion. Once this stops, once this starts, it doesn't stop until there's no more gas left. Here's a simulation showing that. So what I'm showing here is a simulation very similar to the ones that I was showing in the last lecture bite, where we were talking about how planets can open gaps in the gas and the disk and the dust distributions in disks. The reason why this giant planet is opening this gap in the gas is because it's sucking all that gas up. All of that gas is going onto the planet. And then we have these various streams of gas accumulating on, and you can see that these spiral waves are being driven. So this is how we believe that Jupiter and Saturn formed. by really rapidly building up a core thanks to the presence of water and ice form far away from the star, and then sucking up all of the gas in its vicinity until it was a massive planet with about 300 times as much material as there is on Earth. Okay, so that explains why further away from the star, we get these gas giants, these much larger planets that have much more hydrogen and helium gas than the close in planets. So I want to end with a couple of notes on snow lines. We've mostly talked about the water snow line, this region, this dividing line between where water is solid, water is liquid and gas, mostly gas, because in space it's hard to have liquids without much pressure, and where water is solid. But there are other snow lines as well, because there are other materials that can freeze the same way water does. So here's some other examples of snow lines. We have ammonium snow line next further out, carbon dioxide, methane, carbon monoxide, and nitrogen. So all of these will add more material to accumulate together and to build up planets. And they all should affect what the overall composition of these planets is in the end. Because if you build planets in a region out here where there's a lot of carbon monoxide in solid form, you should get more carbon monoxide or carbon and oxygen in your planet overall at the end because it was an active participant in the accretion process. We can actually take images of snow lines. So, for example, here is an image from the ALMA Observatory, another radio image. And what they're looking at here is a protoplanetary disk. And they're looking at a particular species of gas or a particular molecular species. So in particular, they're looking for N2H plus, which is a nitrogen hydride plus, I guess. This material, this molecule, is only abundant in places where carbon monoxide is not, or where carbon monoxide is not present as a gas, because if it's in the same place as carbon monoxide, it will react. And what this does is it means that wherever you see N2H, there must not be gaseous carbon monoxide. And what you can see in this image is that there's a hole in the middle of this disk where there is no N2H. So what we can imagine is that inside of this hole, all of the carbon monoxide must be in gas form because it's now reacted to get rid of the N2H. But beyond this hole, all of the carbon monoxide is frozen, and we get a lot of N2H as a result. So by looking at where the N2H is and where the N2H is not, we can tell where the carbon monoxide is. And we can see that the snow line for carbon monoxide is right around here in this region. The other final note that I want to make is that disks are 3D objects. It turns out that they're not totally flat, and in fact, they flare outwards. So the further away you are from the star, the wider they are, the thicker they are, and it has this kind of curve like this. So what is the consequence of this? It turns out that as a result of this flaring, there really is no such thing as a snow line because different parts of the disk are going to be heated by the star differently. So imagine the star is here and that this is two different sides of the disk, and we're kind of looking at it sliced halfway through. So this is the midplane of the disk, kind of the flat part that we usually think about. But the disk extends upwards, and there's gas and dust up here as well. So imagine that you're looking at a part of the disk right along the midplane. There's a lot of stuff blocking the light from your star that's over here. So this region is going to be relatively cooler than this region up here because less starlight is getting blocked because it's traveling through less material. There's like a lot of gas and dust very close to the center of this disk. So as more light is blocked right along the midplane, that means that the cooler regions are going to be closer to the star. So snow lines are going to be closer to the star and the midplane than they are further out. Up here, where there's really not that much dust or gas blocking the light from the star, this material is going to be hot. So even though it's much further away from the star than this material over here, it will still be in gaseous form. So if there's water up here, it would still be in steam. Whereas even much closer to the disk, much closer to the center of the disk, the water around here will be solid. So really, we don't look at snow lines so much as we look at snow surfaces, because we have this 3D surface, this 3D border between the regions where there's liquid or where there's gaseous water and where there's solid water in the disk.